welcome to Sangam tutorials, SP Gubbi online classes for Ncert and Cbse 10th standard for mathematics and science. So here we are going with the light chapter. This is class 6 where we have already got into the depth of light. So in the last session we have discussed regarding the terminologies connected to spherical mirrors. Very important terms or terminologies connected to spherical mirrors and their definitions. So you should be able to identify those terms and terminologies when you draw a ray diagram. So that is the application. So here among the terms what we discussed in yesterday's class, very important, all the terms are very important. Among them some three are very important. One is the focal length, another is the radius of curvature, and the most important is the principal axis. So let us recapitulate the things and move on to the today's concept. Right. So here, what is the radius of curvature? So it is the radius of the hollow sphere where the spherical mirror is a part of it, is called as the radius of curvature, represented by big letter R, and the line which passes through the pole of the mirror and the center of curvature is called as the principal axis. So that is the line which is taken as a reference for the light rays which are falling on the mirror. The pole of the mirror is which is the center of the mirror, which divides the mirror into two equal parts. So that is called pole of the mirror, which is represented by capital letter P. And then we come for the principal focus, when the light rays which are incident on the mirror, and the light rays are incident on the mirror, they get reflected and they meet at a point, or they appear to meet at a point on the principal axis. So that point is called as the point of convergence with respect to a concave mirror, and point of divergence with respect to the convex mirrors. So that point is represented by capital letter F. So now the distance between the pole of the mirror and the principal focus is called the focal length of the mirror, which is represented by small letter f. So then comes the aperture. Aperture is the surface of the spherical mirror where the incident light falls on it. So aperture may vary from mirror to mirror. That's very important. So then we come for the most important thing again, that is principal axis. You have to remember this. It's a line joining the pole of the mirror and the center of curvature, and which can be extended on both sides for our reference. It is taken for our reference. Okay, with these things we will move on to the today's concept, which is very important. So if you are willing to draw beautiful ray diagrams on spherical mirrors, how the images are formed and what is the position of the images, if you want to learn it and take a grip on that, this class is for you. So you have to listen to me very carefully, look at the ray diagrams what I draw, with supporting to that. Very keen observation is required here. So if you have any questions, you can send me through WhatsApp. I am ready to answer it. So let us go with the today's concept, that is the sign conventions. Very important. Sign conventions for spherical mirrors for their reflection. That is sign convention for reflection by spherical mirrors. So here, when light falls on spherical mirrors, whether it is a concave mirror or it is a convex mirror, the light is going to get reflected. So keeping these things in mind, that is, whenever the incident light is made to fall on a convex mirror or a concave mirror, the light is going to get reflected and they form images. So those images are of two types, virtual images and real images. You know that. So if you want to locate the position and size of that image formed in the mirror, you should be well aware of these sign conventions of reflection by spherical mirrors. So this is very important, sign conventions for spherical mirrors. So where it is required, I will tell you once again. If you draw a ray diagram for a concave mirror or a convex mirror, to analyze, to study the position and size of the image formed, then you should be knowing the sign convection of reflection by spherical mirrors 100%. If you do not know this, if you are not able to cope up with this, right, you cannot learn. You will not be able to learn the ray diagrams perfectly. So I hope you will do it. So this is very easy. It's not difficult. It's very easy. Just 3 statements I am going to give you. Listen to that very carefully. Then the numericals on the spherical mirrors and the ray diagram categories, both the categories, you will be a master in that. Okay, let us go with sign conventions. So now, we have 2 types of mirrors, we know that. That is, one is concave mirror, another is convex mirror. Concave mirror and convex mirror. So here I will go with the definition of concave mirror and convex mirror once again. So a concave mirror is a spherical mirror where its surface it's not a plane mirror, it's a part of a hollow spherical mirror. A concave mirror is a part of a hollow spherical mirror where the outer surface will be silvered so that its inner surface will be a reflecting surface. So this is a concave mirror. So what about a convex mirror? A convex mirror is also a part of a hollow spherical mirror in which the inner surface will be silvered so that the outer surface becomes highly reflecting. So this is called as a convex mirror. So these are the definitions for concave mirror and convex mirror. So we will first we will go with the concave mirror. Let us study the sign convections of concave mirror of reflection by using some ray diagrams. Now, let us take the concave mirror here. So this is the concave mirror. So we know that its outer surface is silvered. Totally, its outer surface is silvered. So this will be the pole of the mirror. This is the pole of the mirror, and let us take this as the center of curvature of the mirror because it's an imaginary sphere here. So this imaginary sphere's center is called as the center of curvature. So let us join this center of curvature and the pole. So when I join these 2 points, you call this line as the principal axis. So let us extend it on both sides. I will extend this on this side and I will extend this on this side also. Okay, so this becomes the principal axis. This is the principal axis. So this is the center of curvature for our reference. Okay, now I am going to keep an object. So objects, we know that there are 2 types. One is a point-sized objects which are represented by a dot. A point-sized objects which are represented by dot, and the big size objects, bigger objects. So they are represented by an arrow mark which is directed upwards. So let us imagine that this is the object. Let us take it as object AB. So this is the object. It's a bigger object. So therefore I am going to represent that by an arrow mark which is directed upwards. It's a ray which is directed upwards. So this is the object AB. Now, so here it is at point B. The object is at point B on the principal axis. Now, here from the object, the light starts traveling towards the mirror. So, from the object, let us imagine the light starts traveling towards the mirror, and let us take this as a light ray which is traveling that is parallel to the principal axis. The light ray is traveling from the body, that is body AB, that is object AB, towards the mirror which is parallel to the principal axis. Now, here, what is the distance of the object, that is AB, from the mirror? What is the distance of the object AB from the mirror? So, keep the rule here, I am telling you now. Any distance of the object from the mirror is measured from the pole of the mirror. That is measured from pole, not from here, not from here, not from here. The object distance, that is the distance of the object from the mirror, is always measured from the pole of the mirror. This is rule number 1, you have to remember this. So any distance, whether it is an object distance or if it is a image distance, whatever it may be, if that particular distance will be measured from the pole of the mirror. So all distances are to be measured from the pole of the mirror. So this is the direction of the incident light ray. So light rays are moving in this direction. So you are measuring from here to here. So any particular object, that is object distance from the mirror is to be measured from the pole of the mirror. As you are measuring from in this direction, the incident light rays are moving in this direction. That means your measurement is being done in the direction opposite to that of incident light rays. In the sense, the incident light rays are moving in this direction, you are taking a measurement from this direction. So you are opposite. You are doing it opposite. Right? So therefore, the object distance as you are measuring in case of a concave mirror, as you are doing opposite to that of the direction of incident light rays, therefore object distance will be taken here as negative. Because if you measure any distance opposite to the direction of incident light rays, then it is negative. So remember this. So you are measuring from the pole of the mirror. So you are measuring in this direction, but the incident light rays are moving towards the mirror in this direction. So as your measurement is opposite to that of the direction of the incident light rays, therefore the object distance here becomes negative. Keep this in your mind, it's very, very important. So object distance is negative. Please remember, in case of concave mirror, object distance is negative. Why I am stressing this, why I am telling you again and again, because I can see what are the things you require while drawing ray diagrams and solving numerical problems. I know that, therefore I am telling you these things are very important. You have to remember this. Right? So object distance is negative. For example, let us go with the next step. Let us imagine the image is formed somewhere here. I don't know exactly. The image is formed somewhere here. Let us take it as A dash and B dash. The object's image is formed here. So how it is formed there, how it is that is inverted, all those things without any doubt of being doubtful, I am going to teach you in the next session. Wait until that, it's just an example. So AB is the object, you are measuring from the pole of the mirror. So as you are measuring it in the direction opposite to that of the incident light rays, therefore object distance is negative. This is first concept. Let us go with the second one. Let us imagine the image of this particular object is formed here. So this is A dash, B dash, just to differentiate I am giving different names. So as I told you in the first point, anything what you measure in a mirror should be measured from the pole of the mirror. So therefore, let us measure this distance. Again you are measuring this distance from the pole of the mirror, which is opposite to that of the direction of incident light rays. Therefore, image distance is also negative here. So image distance is negative. So keep this rule I am telling you. If all the distances from the mirror are to be measured from the pole of the mirror. If you are measuring anything, that is the object distance or the image distance, and if you are measuring it in the direction opposite to that of the incident light rays, then that value, that distance what you measure in centimeters or meters, whatever you measure it, that distance, whatever you measure it, that value should be taken as negative. Please keep in your mind. So object distance here is negative, image distance is also negative. So in some of the ray diagrams, you may get the object here also, maybe here also. So here, when you go with this, you are measuring. If you consider the object is somewhere here, so you can take it as A dash, B dash. Okay, let us take it. There is one of the consequence. So as you are measuring this image distance from the pole of the mirror here, so it is along the direction of the incident light rays. So incident light rays are coming in this direction. We are also measuring this image distance in the direction of the incident light rays. Therefore, this distance should be taken as positive. So all the distances from the mirror are to be measured from the pole of the mirror. First point. Second point, if you are measuring anything opposite to the direction of the incident light rays, then that value what you get will be negative. That should be taken as negative. So now third point, if you are measuring any distance along the direction of the incident light rays, that is in the same direction as the incident light rays, then that should be taken as positive. Very important. Many students I have seen, sir, after this class they tell me, sir, I understood everything, it was very nice. When I start solving problems, numerical problems related to optics on board, they start doing silly mistakes. For plus sign they will take minus, for minus they take plus, and some students will be totally confused which sign to be taken. So therefore, it's very important, I am telling you. Please follow this. So this is all. Now this is the principal axis. This is the principal axis. Any measurement, that is AB, I told you it is the object. So here this is the height of the object. This is height. AB is the height of the object. So you have to measure the height of the object in this direction. So if you measure anything above the principal axis, if you measure anything above the principal axis, that will be positive. So above the principal axis is positive. Remember this. So naturally, below the principal axis, whatever you measure, that should be taken as negative. So this is negative. So anything you measure above the principal axis is positive. Anything you measure below the principal axis, this is the principal axis, and below this whatever you measure it, then it is negative. Below, above the principal axis, whatever you measure it, that is taken as positive. So here I can guess your answer here. What is the length of A dash B dash? What is the height of A dash B dash? If I ask you, sir, the height will be negative. Whatever the height may be, that height will be negative because this image is formed below the principal axis, therefore it should be taken as negative. So with me, I am having 5 statements now. I have 5 statements. I will repeat this once again. What all the distances you measure from the mirror, whether it is a concave mirror or a convex mirror, all the distances should be measured from the pole of the mirror. First point. I will go with the second point. What if you are measuring a distance in the direction opposite to that of the incident light rays, then that value what you get should be taken as positive. So that is negative. That is negative because you are doing it opposite to that of incident light rays. Now, what if you are measuring a distance along the direction of the incident light rays, then that should be taken as positive. Here you can see this. Here you can see this distance we are measuring in the direction of the incident light rays. Therefore, this distance will be positive. 3 statements are over. I will go with the 4th statement. If you are measuring the height of the object, height of anything above the principal axis, then that height will be positive. And if you are measuring any height, that is the height of the image which may be formed below the principal axis, that is below this, then this height will be, the value of this height will be negative. So these are the very important 4 sign convections for concave mirrors. Let us go with convex mirrors. Same thing happens here also. Let us take a convex mirror. So this is the convex mirror. So this is rough surface, silvered. So therefore the outer surface will be the reflecting surface and the inner one will be silvered. So this is the whole of the mirror. So this becomes the center of curvature. This becomes the center of curvature. I will Join these 2 points. This becomes the principal axis. I will extend it on both the directions. I will extend the line on both the directions. So this is the center of curvature. This is pole. Right. Now we will go with the sign conventions again. One by one we will go. For example, I have placed the object, that is AB, in front of the mirror, because object cannot be placed inside the mirror. Therefore, the object is always placed in front of the mirror to obtain the image. So as I told you, in case of concave mirrors, all distances should be measured from the pole of the mirror. So let us imagine the light rays are traveling in this direction from the object. It's falling on the object, that the light rays are falling on the mirror. So this is the direction of incident light rays. Now you are taking the measurement from the pole of the mirror to, that is P to B. So you are going from P to B. So as you are going from pole of the mirror to the object, you are taking this measurement opposite to the direction of the incident light rays. So therefore, this measurement will be positive or negative? It will be negative, because you are measuring something against the direction of incident light rays. Therefore, it is negative. So this value is negative. Okay. Let us imagine, right, the image is formed somewhere here. Image is formed, that is A dash, B dash. Somewhere some image is formed. Now, I want to measure the distance of the image from the pole of the mirror. So here, if I measure this distance from the pole of the mirror, I am measuring something along the direction of the incident light rays. Incident light rays are going in this direction, I am measuring in the same direction. Therefore, this value will be positive. Very important. This value will be positive, because I am measuring that distance along the direction of the incident light rays. Therefore, this value will be positive. Now, what is the height of AB? Height of AB is positive. Very simple, because it is measured above the principal axis. So, what all the measurements you do above the principal axis is taken as positive. So, here also, as you are taking the measurement above the principal axis, so this measurement, this length from B dash to A dash, this length will be positive. So, if the image, for example, I am telling you, if the image is formed below the principal axis, so this distance is negative, taken as negative, because you are measuring something below the principal axis. So, 4 statements again. Same sign conventions are applied for same sign conventions. No changes at all. Same sign conventions are applied same to same for concave mirrors as well as convex mirrors. No changes, no differences. Same to same. Alright. So these are the sign conventions for reflection by spherical mirrors regarding concave mirrors and convex mirrors. So I would like to repeat once again, a little bit fast. Listen to me very carefully. All the distances should be measured from the pole of the mirror. If you are measuring something against the direction of the incident light rays, then that should be taken as negative. If you are measuring something along the direction of the incident light rays, then it is taken as positive. If you are measuring something, that is height of the objects or height of the image, something, whatever it may be, if you are measuring it above the principal axis, then it should be taken as positive. If you are measuring the height of an object, that is height of an image, which is below the principal axis, then it should be taken as negative. Right? Along the direction of light rays, positive. Opposite to the direction of light rays, negative. Above the principal axis, positive. Below the principal axis, negative. And all the distances are to be measured from the pole of the mirror. Right? I hope you got this. Let us go with the next concept. Now let us go with the relationship between curvature. That is R, represented by R, radius of curvature of a mirror, and its focal length. That is F. So now, there is a very simple relationship between radius of curvature R and its focal length F. So it applies for all mirrors, whether it is a concave mirror or it is a convex mirror. For both the mirrors, this relationship applies. Right. Let us go with this. Let us take a concave mirror. I'm going to take a concave mirror. So it is that is silvered at the outer surface. Therefore, the inner surface is highly reflecting. So this is the pole of the mirror. So this is the center of curvature. So I will join these two lines and extend it on both sides. I will extend it on both sides. Okay. So this is the pole of the mirror and this is center of curvature. Right now. So it's a very important derivation. This is not for your exams, but I am not teaching you for your exams. I am teaching you physics for your life. For your lifetime, you should remember physics, and you should be able to teach and convince physics for your juniors. That's my aim. Learn physics for your life. Enjoy it. So exams, sorry, you will come for the exams. For how many marks? Sir, is this important? Is this most likely for the exams? No business like that. This derivation, that is the relationship between the radius of curvature and focal length, is not for your syllabus, but I just wanted to tell you the exact relationship between the radius of curvature and focal length. How they are related. See, somebody has done something, using that it's not a greatness. Right? Knowing how it is done and using it is the beauty of it. I hope you understand. Okay, let's go with this. So, relationship between radius of curvature and its focal length. I have taken an example of concave mirror. You can also take convex mirror for the derivation. So, concave mirror is little bit friendly, so therefore I have taken this. So, this is the pole of the mirror, this is the center of curvature. So, now let us imagine a light ray is falling on the mirror at some point on it. So let us call it as point A. So this is B. So BA is the ray of light falling on the mirror. Right. So now this light ray, let us imagine that it is parallel to the principal axis. For the principal axis, this light ray is exactly traveling parallel to that. Now, so here, this particular light ray, after reflection from the mirror, 100% it passes through the principal focus. That is principal focus, that is F. It passes through the principal focus, right? The point at which the light ray after reflection meets the principal axis is called as the principal focus. That is represented by F. That's very important. Now, here I am going to draw a normal from C to A, the center of curvature. I will draw a normal here. This is not a normal ray, it is just a normal. Okay, this is the normal at the point of incidence. So let us take this as again point A. Now, the incident light ray is traveling parallel to the principal axis. After reflection on the mirror, is going to pass through the principal focus. Right? I hope you understood the sequence. Now, I have drawn the normal. So at this point, this is called the point of incidence. You should remember the laws of reflection now, and you have to apply this. So this is the point of incidence. So AB, that is BA, is the incident light ray, and this is the normal. So and we know that according to the law of reflection, the angle between, that is this angle, the angle between the incident light ray and the normal is called the angle of incidence. That I am going to represent it by small letter I, and the angle between, this is the angle again here, the angle between, right, the reflected light ray and the normal is called the angle of reflection, that is R. So this angle will be exactly equal to this angle according to the law of reflection. So as I told you earlier in the previous classes, that laws of reflection are obeyed by plane mirrors as well as spherical mirrors, right? So sir, it is a spherical mirror, light falls on it, laws of reflection is getting applied. How it is possible? So I will tell you one very important statement. Remember this. Every point on a spherical mirror, acts like a plane mirror. So this point is a small plane mirror. So when the incident light ray falls on the plane mirror, it is going to get reflected. When you draw the normal, which is perpendicular to the plane, to this plane you are drawing the perpendicular. So therefore the angle of incidence will be equal to the angle of reflection. Hence mirrors obey laws of reflection. Okay, let us go further. So now here incident light ray and the principal axis, they are exactly parallel to each other. I have drawn this. So now according to the law of reflection, and that is angle BAC, this angle is equal to angle CAF, this angle, right? So let AB be the incident light ray, okay, not AB, it is BA. Let BA be the incident light ray, and let us take a point here. So let AC be the reflected light ray, okay, very important. And let CA be the normal. I can again see, okay, let us take it D. So AD be the reflected light ray, let CA be the normal, and CA be the normal. So therefore, according to laws of reflection, angle BAC, that is this angle BAC is equal to angle CAF. So this is the one thing. Now here BA and CP, these two lines are parallel to each other. These two lines, that is BA and CP, are parallel to each other. So therefore angle BAC, that is this angle, will be equal to angle ACF, that is this angle. Because here for these two parallel lines, this line is going to act as a transversal. So when you draw a transversal for two parallel lines, then we know that in our previous theorems in geometry we have learned that alternate angles will be equal. So therefore angle BAC is equal to angle ACF. Angle BAC is equal to angle ACF. So this is according to laws of reflection. This is the reason, according to the laws of reflection, and for this is alternate angles. This is the reason for that. Okay. So now we have two angles equal. So this angle is equal to this, and this angle is equal to this. So therefore this angle is equal to this angle, and this angle is equal to this angle. So in the sense, this is equal to this, and this is angle is also equal to this. In the sense, two things are equal to the same thing. So according to the axiom on geometry, if two things are equal to the same thing, then they should be equal to one another. So therefore angle ACF, that is this angle, should be equal to angle CAF, this angle. So therefore angle ACF is equal to angle CAF. CAF. So it's an axiom. Okay, anyway, right. So as these two angles are now equal to each other, therefore in triangle ACF, I hope you can see this triangle now. So in this triangle ACF, in triangle ACF, two angles have become equal. So in your previous classes you have come across this proposition as a theorem. We have proved this. So in a triangle, if two angles are equal, then it is an isosceles triangle, and the sides which are equal to the sides which are opposite to the equal angles are also equal. So opposite to this angle is this side, and opposite to this angle is this side. So therefore CF is equal to AF. CF is equal to AF. So triangle ACF is isosceles. Triangle ACF is isosceles. So therefore CF is equal to AF. CF is equal to AF. So because angle A is equal to angle C. Angle A is equal to angle C, so therefore CF is equal to AF. This is very important. Now, we will go with a small conclusion. Right. So, the mirror what I have taken as a concave mirror here, it's having a very small aperture. Very small aperture. So in yesterday's class I have told you what is an aperture of a mirror. The part of the spherical mirror where the incident light falls on it is called as the aperture of the mirror. So here for this mirror the aperture is very small. So as this aperture is very small, this point A, let us imagine that point A coincides with point P. That is, point A coincides with point P. So now as A and P coincide, as aperture of concave mirror is small, as aperture of concave mirror is small, so therefore A and P, points A and P coincide. Points A and P coincide. So A and P they coincide. Let us imagine that. So this side is equal to this side. As point A coincides with P, then this AF becomes equal to FP. This AF becomes equal to FP. Right? So therefore, very important, AF equal to FP. Very important. AF becomes equal to FP. This is FP. This is AF. So as A coincides with B, this entire AF coincides with this. So therefore AF becomes equal to FP. Now let us go with the next thing. So therefore CF is equal to, let us define CF, the length of CF here. So length of CF can be defined as CP minus FP. CP minus FP. CP minus FP, that is entire CP, from entire CP if you remove PF you get CF. So that is CF here. So now another conclusion also we can come here. So AF is equal to FP. As AF is equal to FP, then CF is also equal to FP. CF also becomes equal to FP. CF is equal to FP. So once again, these two sides are already equal. As the aperture of the concave mirror is very small, this coincides like this. So AF becomes equal to PF, that I have written there. So already AF is equal to CF, that we have already proved here. So therefore this is equal to this, and this is equal to this already, so therefore this becomes equal to this. So once again, this is equal to this, just we have proved that, but already this is equal to this, so therefore this length becomes equal to this. Right, that's the analogy here. So CF is equal to FP. So CF is equal to, let us take FP here, instead of CF we will take FP. So FP is equal to CP minus FP. So we will take this FP to the LHS. So FP plus FP is equal to CP. So now 1 FP plus 1 FP is 2 FP is equal to CP. Now let us see what is FP in the ray diagram. So here in the ray diagram, FP is nothing but, here F is the principal focus and P is the pole of the mirror. The distance between the principal focus and the pole of the mirror is nothing but the focal length of the mirror. That is very important. So that is 2 FP, that becomes 2 into FP is focal length, which is equal to, what is CP here? CP is the center of curve, that is radius of curvature. From C to P, if you take the measurement, that is the radius of curvature. So that is R. So here F is equal to R by 2. That is focal length is always half the radius of curvature. Focal length is always, that is this focal length is always half the radius of curvature. So this is the radius of curvature and the principal focus will be always at the center, joining the center of curvature and the pole of the mirror. That is this length F, what we get as focal length, it is always half the length of CP. That is the focal length is always half the radius of curvature. So you have to remember this, F is equal to R by 2, or you can go with this, R is equal to 2F. You can also use this formula, wherever it is required. So this is the relationship between the radius of curvature and the focal length of the mirror. So this rule applies, this formula is valid for both the mirror type of mirrors, that is concave mirror as well as convex mirrors. Right. So now we have understood the relationship between the focal length and radius of curvature. So F is equal to R by 2 or R is equal to 2F. For example, one more question may come on this very simple formula. For example, I will go with this. Find focal length. Find focal length of A concave mirror. Find focal length of a concave mirror whose radius of curvature is 30 centimeters. Find focal length of a concave mirror whose radius of curvature is 30 centimeters. Right, so that here radius of curvature is given as 30 centimeters, you have to find the focal length. So it is mentioned that it is a concave mirror, 100% it is a concave mirror. So in a concave mirror, focal length is always positive or negative? It is always negative, because in a concave mirror, if this is the principal axis, this is the pole of the mirror, and this is center of curvature, and this is the principal focus, and the distance between P and F is focal length, and you are measuring opposite, the direction opposite to that of the incident light rays. Therefore, F is negative. This is how we have to analyze. So F is equal to R by 2. So F is equal to R is 30 centimeter by 2. That comes to 15. Therefore, F is equal to minus 15 centimeters. So how this minus came? Sign convections for spherical mirrors. So this is how I have shown you. When you measure from pole of the mirror to the principal focus, that is called focal length. You are measuring in the direction opposite to that of incident light rays. Therefore, F is negative. So this is very important. Okay. 1 mark questions like this may be asked in your examinations. Okay. So now we'll go with the very important topic. Very important topic now. So I am going to tell you 4 rules required for drawing ray diagrams. You should remember these 4 rules before drawing ray diagrams. Very important. You should remember this. You should always recapitulate yourself, right, while before entering into numericals or ray diagrams. Right? Let us go with this. Rule 1. Rules for drawing ray diagrams for concave mirror or it is convex mirror, whatever it is. Right. Rule 1. Imagine a concave mirror. So it is silvered outside. This is the principal axis, pole of the mirror, radius of curvature. So rule 1. If a light ray is travelling parallel to the principal axis and falls on the mirror, gets reflected and passes through the principal focus. Remember this. Whenever a light ray which is travelling parallel to the principal axis after reflection passes through the principal focus. Very important. So we will go with the convex mirror here. Right. So this is the convex mirror. So this is the principal focus, the principal axis. So this is the pole of the mirror. So let us imagine a light ray falling on the mirror. So it is travelling parallel to the principal focus, that is principal axis. This is the light ray which is going to get diverged, that is diverging light ray. So this particular light ray, when extended backwards, it appears as though it is passing, it is starting from the principal focus of the convex mirror. So very important, whenever a light ray travelling parallel to the principal axis after reflection, right, passes through the principal focus in case of a concave mirror. So this is for concave and this is for convex, right. So whenever a light ray travelling parallel to the principal axis after reflection, it gets diverged. This diverging light ray appears as though it is coming from the principal focus, which is located beyond the, that is behind the mirror. So this is rule 1, you have to remember this. Once again, any light ray for both the mirrors which is travelling parallel to the principal axis after reflection, 100% it passes through the principal focus. In this case, and it appears as it passes through the principal focus in this case, that is convex mirror case. Let us go with rule 2. Let us go with this. Now, let us imagine a convex mirror, sorry, concave mirror. So this is that is silvered surface. This is the pole of the mirror. This is the principal focus, and this is the radius of curvature. Principal focus always should be the midpoint between the center of curvature and the pole, because just we have derived, that is r is equal to f by 2. That f is equal to r by 2, so therefore this half will be equal to this half. Very important. Now let us imagine we do not know from where the light ray is coming. One light ray, it is travelling exactly through the principal focus. From somewhere the light ray is coming and it is travelling through the, passing through the principal focus. The light ray which is passing through the principal focus of the mirror, it is going to get reflected by the mirror. Then what happens? Then the light ray is going to travel exactly parallel to the principal axis. Exactly parallel to the principal axis. So remember this, when a light ray travelling parallel to the principal axis after reflection passes through the principal focus. If a light ray travelling through the principal focus after reflecting starts travelling parallel to the principal axis. So this cannot be shown for concave mirrors. This cannot be shown for concave mirrors because the light ray doesn't pass behind the mirror. That's the point here. let us go with rule 3. Rule 3, very important. Let us go with this. Let us imagine a concave mirror. Imagine a concave mirror. So it is silvered outside. So this is the pole of the mirror. This is the principal axis. So this is the center of curvature. Midpoint is the principal focus. So everything is ready now. If a light ray coming from somewhere, you do not know from where it is coming. Somewhere it is coming. It is traveling through the center of curvature. It is traveling through the center of curvature. So if a light ray is traveling exactly through the center of curvature and falls on the mirror, then what happens? Then what happens? So this is very important. So if a light ray coming from somewhere passes through the center of curvature of the mirror, it gets reflected by the mirror and it is bounced back again in the same direction and it passes through the center of curvature again. This is very, very important. The light ray may be coming from this direction also, no problem. So it is passing through the center of curvature, it hits the mirror, it gets reflected in the same direction. In the sense, it is going to get bounced back to the same medium, right? It's very, very important. Now, if a light ray, same thing, I will tell you rule 3 itself, I will include this. If a light ray is traveling along the principal axis, it hits the pole of the mirror and again travels back in the same medium, right? Two things happens in the same manner. One light ray is traveling through the center of curvature, gets reflected by the mirror and bounces back to the same medium in the same path. It isn't going to change its path. Same way, same thing, as the light ray passes along the principal axis, hits the pole of the mirror and bounces back to the same medium. Because if a light ray is traveling through the center of curvature of the mirror, while getting reflected at this point of the mirror acts like a plane mirror, as though the light is falling normally on the spherical mirror. So what happens when the light ray falls normally on a plane mirror? It is going to get reflected and moves back in the same direction, because the angle of incidence will be 0 and angle of reflection will be 0. So therefore same thing happens in rule 3 also. So this is, you have to remember. Next we will go with rule 4. Rule 4, very important. So let us imagine a concave mirror, so which is, this is the principal axis, this is the pole of the mirror, this is the center of curvature, midpoint is principal focus. Many of the teachers who are teachers, they tell you have to mark the principal axis at the center of C and B. You mark it. Sir, why we have to mark it? No, you have to mark it. So don't, why these things happening? Why we should take it like that? See, this is, you have to do a research. You have to try to learn it. That's very important. Now, let us go with the rule 4. Let us imagine a light ray is traveling oblique to the principal axis. This is the principal axis and the light ray is traveling obliquely to that, not parallel to that. So usually we take all the light rays in all the examples parallel to that, leaving this. But here, let us imagine a light ray traveling obliquely to the principal axis. So here, this light ray is going to fall on the pole of the mirror. It is going to get reflected at this point. Then what happens? So if a light ray traveling obliquely to the principal axis falls on the pole of the mirror after reflection, what happens? So here, the light ray after reflection, it is going to move back in a particular direction such that this angle will be equal to this. So you have to remember this. In one of the ray diagrams, we are using this. So these are the 4 rules which are very much required for drawing ray diagrams, and the sign conventions what you have discussed earlier are very much required for solving numericals on mirrors. So all the four are very important. I will repeat it once again. If a light ray traveling parallel to the principal axis after reflection passes through the principal focus. If a light ray is traveling through the principal focus and falls on the mirror, then after reflection it travels parallel to the principal axis. The third rule is that if a light ray is passing through the center of curvature of the mirror, then after reflection it is going to retrace its own path. That's very important. And the fourth rule is if a light ray is traveling obliquely to the principal axis after reflection, then after reflection at the pole of the mirror, right, it makes an angle which is equal to the angle between the principal axis and the incident light ray. So that means this angle will be equal to this. So these are the four rules. So I hope this is a very important class. Out of all the classes what you have done until now, this is the most important class, because all the coming classes or in all the coming sessions, these things will be recalled again and again and again wherever it is required. So if you want a grip on this, good grip on this, go through the video 2 times, 3 times until you are a master in that. So if you have any doubts regarding this, you can call me back, right? So I hope you enjoyed the entire session. So this was a very challenging session for teachers and also for students to learn it. So once you learn it, you are a master in this. You will start really enjoying the light chapter, right? So until now, you have come across many sessions. So in this session, please go with the textbook. In the textbook, it is beautifully given. In the Ncert textbook, it is given. So please go through this. So stay home, stay safe, and keep learning. Thank you very much.